Scientists just cracked a quantum puzzle. New strategy reveals full chemical complexity of quantum decoherence. Topics: Popular quantum chemistry, quantum materials, quantum physics. University of Rochester. By University of Rochester, December 22, 2023. Rochester researchers have reported a strategy to understand how quantum coherence is lost for molecules and solvent with full chemical complexity. The findings open the door to the rational modulation of quantum coherence via chemical design and functionalization. Credit: Annie Ostad de la Font. The findings can be used to design molecules with custom quantum coherence properties, laying the chemical foundation for emerging quantum technologies. In quantum mechanics, particles can exist in multiple states at the same time, defying the logic of everyday experiences. This property, known as quantum superposition, is the basis for emerging quantum technologies that promise to transform computing, communication, and sensing. But quantum superpositions face a significant challenge: quantum decoherence. During this process, the delicate superposition of quantum states breaks down when interacting with its surrounding environment. The challenge of quantum decoherence. To unlock the power of chemistry to build complex molecular architectures for practical quantum applications, scientists need to understand and control quantum decoherence so that they can design molecules with specific quantum coherence properties. Doing so requires knowing how to rationally modify a molecule's chemical structure to modulate or mitigate quantum decoherence. To that end, scientists need to know the spectral density, the quantity that summarizes how fast the environment moves and how strongly it interacts with the quantum system. Breakthrough in spectral density measurement. Until now, quantifying the spectral density in a way that accurately reflects the intricacies of molecules has remained elusive to theory and experimentation. But a team of scientists has developed a method to extract the spectral density for molecules and solvent using simple resonance Raman experiments, a method that captures the full complexity of chemical environments. Led by Ignacio Franco, an associate professor of chemistry and of physics at the University of Rochester, the team published their findings in the Proceedings of the National Academy of Sciences. Linking molecular structure to quantum decoherence. Using the extracted spectral density, it is possible not only to understand how fast the decoherence happens, but also to determine which part of the chemical environment is mostly responsible for it. As a result, scientists can now map decoherence pathways to connect molecular structure with quantum decoherence. Chemistry builds up from the idea that molecular structure determines the chemical and physical properties of matter. This principle guides the modern design of molecules for medicine, agriculture, and energy applications. Using this strategy, we can finally start to develop chemical design principles for emerging quantum technologies, says Ignacio Gustin, a chemistry graduate student at Rochester and the first author of the study. Resonance Raman experiments, a key tool. The breakthrough came when the team recognized that resonance Raman experiments yielded all the information needed to study decoherence with full chemical complexity. Such experiments are routinely used to investigate photophysics and photochemistry, but their utility for quantum decoherence had not been appreciated. The key insights emerged from discussions with David McCament, an associate professor in the chemistry department at Rochester and an expert in Raman spectroscopy, and with Chong-Woo Kim, now on the faculty at Cheonam National University in Korea and an expert in quantum decoherence, while he was a postdoctoral researcher at Rochester. Case study: thymine decoherence. The team used their method to show, for the first time, how electronic superpositions in thymine, one of the building blocks of DNA, unravel in just 30 femtoseconds. 1 femtosecond is 1/millionth of 1/billionth of a second, following its absorption of UV light. They found that a few vibrations in the molecule dominate the initial steps in the decoherence process, while solvent dominates the later stages. In addition, they discovered that chemical modifications to thymine can significantly alter the decoherence rate, with hydrogen bond interactions near the thymine ring leading to more rapid decoherence. Future implications and applications. Ultimately, the team's research opens the way toward understanding the chemical principles that govern quantum decoherence. We are excited to use this strategy to finally understand quantum decoherence in molecules with full chemical complexity and use it to develop molecules with robust coherence properties, says Franco. Reference: Mapping Electronic Decoherence Pathways in Molecules by Ignacio Gustin, Chong-Woo Kim, David W. McCament and Ignacio Franco, November 28, 2023, Proceedings of the National Academy of Sciences. Scientists just cracked a quantum puzzle. New strategy reveals full chemical complexity of quantum decoherence.